So guys, welcome back to the video series on electrical measurements. So today in this video we'll be discussing about power and energy measurements. So basically we'll be discussing about watt meters and energy meters. Okay, so this is all about power and energy measurements, right? So we have already discussed about watt meters in our previous class. So I think we have already discussed about the electrodynamic instrument, which can be used as a watt meter as well, right? So here we have seen that in an electrodynamic instrument we have two fixed coils. Let's say this is our fixed coil and these two are fixed coils, and we have a rotating coil as well, right? So let's connect it over here, and let's say we have another coil which can be rotated. Let's say we can draw it like this. So this is the movable coil or the rotating coil. So we'll attach a resistance as well, because this coil is generally used as the for voltage measurements. So we'll be connecting the voltage across this coil. Let's call this terminals as V1, V2, and let's call this as C1, C2. This corresponds to, C1, C2 corresponds to the current coil, and V1, V2 will corresponds to the pressure coil. So this is the this is our general wattmeter, and we know that this coil is in such a way that this coil will be attached to the pointer, and this can rotate in any direction depending upon the magnetic fields, right? And we'll be also having a spring which can control it. So that is how this coil is generally designed. So these are air core stuffs. So basically we are looking at electrodynamic wattmeter. So let's say you have a load, right? And you have a source. So let's see how this load can be connected with the source, right? So let's say plus minus so from here our current coil will be in series, and the pressure coil will generally be in parallel connection. This is how we connect our wattmeter. So this is the entire wattmeter, and we have the load over here, right? So you can call this as current coil CC and pressure coil PC, right? So this would be point C1, C2, V1, and V2. These are the four terminals that comes out of the wattmeter. Now here what we can see is that our deflecting torque is actually equal to the IF. You can call this as let's say this is IF, and the pressure coil one as IM. So IF into IM into dm by d theta, and the controlling torque can be given as k theta. K is the spring constant with theta as the angle. At equilibrium you will get that k theta is proportional to the time average of IM and IF, where these quantities corresponds to IM will correspond to the voltage across it, and IF will correspond to the current that is flowing through the current coil, right? So this basically gets the average of a product. This instrument generally gets the average of a product. Now here we know that IM can be written as the time average. Now theta here can be written as the proportional of time average of V of t. Let's say this is the V of t by R, where R is the Rm is the resistance of the pressure coil, into the current I of t. So let's say this is the current, that is I of t, that is flowing through the circuit, right? So here we get the here we can see that this theta is again, R is a constant, so this is again the time average of V of t into I of t, right guys? So this is how we this instrument has been calibrated in such a way that it shows the power, which is the average power. This is the average power, right? Average power consumed, right? So this is how the instrument actually finds the average power consumed in this circuit. Now the major problem here is that one of the major problem that we'll face in this case is that let's look at the problems in this connection. Now here we can see that there is a current IM that is flowing, right? So let's say the wattmeter reading, let's call the current through the current coil as ICC. ICC is the current through the current coil. So here ICC will correspond to IR plus IPC. Let's say IPC is the current through the pressure coil, right? IR is the, let's say this is your resistance R, let's call this IR. This is IPC, which is the current through the pressure coil, and this we can call as ICC, the current coil, right? So here we know that the wattmeter reading is actually proportional to the average of ICC into VPC, right? The pressure coil voltage and the current coil, the current through the current coil, right? So this is how we have designed the wattmeter, and now here we can see that this could be approximately equal to IR VR if and only if IPC is small in comparison to IR, because ICC consists of IR plus IPC. So here this is the error that we have. IPC is the error that we have. IPC into VPC would be the error. So if we can substitute that as IPC into VPC, so you'll get it as the wattmeter reading is proportional to IR plus IPC into VR, that is equal to VR into IR plus VR into IPC. So this is the pressure coil power error in the measurement, and this is our load power, right? Now let's say we change the connections. Let's say we now have a different connection, right? Plus minus V of t, and let's say we have the pressure coil like this, and this is a load, this is our current coil, this is a pressure coil. Now in this case also again we'll face the same problem. Here the current ICC, which is the current through the current, will be same as IR, but the voltage that is across VPC or the pressure coil will consist of the voltage across the current coil as well as the resistance. That is the major difference over here. So here if you look at the wattmeter reading, what we get is that we get ICC into VPC, ICC into VPC is our wattmeter reading, and here ICC into VPC can be written as VCC plus VR. So here if we expand this, you get it as ICC into VCC plus ICC into VR. That is the wattmeter reading. Now here ICC into VR is our load power, is the load power that we wanted to measure, is the desired quantity, and this is the error. So the current coil power error, right? So here also if the value of RCC, the resistance of current coil, if it is very low, then VPC will be approximately equal to VR, and we can neglect the error in this case. But that is not the case every time, so we need to do something in order to compensate this, right? So let's look at how this can be compensated in order to get a better let's say a better circuit, right? So let's look at how this compensation can be done, or to get a better reading measurement, right? So we know that electrodynamometer coils are generally air cored. They don't generally they don't have any core, but let's assume there is some kind of a core, because that would be easier for me to make you understand. So generally it doesn't have any core, but in order to show the compensation winding, let's assume that it has some core, right? Once we finish drawing, you'll be able to understand that why this was assumed. So let's say this is our source, and this is our current coil, right? So let's draw the current coil. Right, so this is our current coil, and let me draw the pressure coil. So the current in the current coil is in this direction, right? Now let's draw the pressure coil. So this pressure coil is also mounted on the same core, right? So let me draw this coil. Now the current will flow in this direction in the pressure coil, right? So here you can see the current direction is opposite in the pressure coil, and let's say the pressure coil definitely has a different coil, but it has windings which is also in the same it has a compensating winding that is on the same core of current coil. And then you have the actual pressure coil and your resistance. So this winding over here on the core is actually known as a compensating winding, right? And we'll see why this is called as a compensating winding very shortly. So here is our load resistance, right? And so this is, let's say this is IR, and now we can see here that and the current that is measured by the current coil, so this is our current coil, ICC, is the sum of IPC plus IR, right? Because this is ICC that is coming over here, this is IPC that is leaving from through this branch, and this is your IR. So it is the sum of IPC and IR in this case. Now if you look at the magnetic field generated by the current coil, in this case the magnetic field generated by the current coil and the compensating coil together, in this case, is directly proportional to what? ICC minus IPC, because there are two currents. This is one current which is ICC that is flowing in one direction, and IPC here is flowing in the opposite direction. So the magnetic field that is jointly produced by this current coil and with this compensating winding would be proportional to the current that is ICC minus IPC, isn't it? Because IPC is the current that is flowing over there, and ICC is the current through the current coil. So which can be written as, where ICC is the sum of IPC and IR. So here if you look at this values, you get ICC can be written as IPC plus IR plus IPC, and then you have a minus IPC, so which is equivalent to IR itself. So this is how we compensate the extra current that is there in ICC by using a compensating winding along with the current coil. Right, now the voltage coil current is the total resistance of the compensating coil plus the voltage coil, and the voltage across VPC would be proportional to VR in this case, and the torque would be proportional to the torque generated by the instrument would be proportional to IR into VR, because it is proportional, since it is proportional to ICC into VPC, right? So this is how we compensate this error in the wattmeter. Now let's look at the energy meter, right? So in energy meter, in the very first class, we had shown a small video of aluminum disc. Let's say you have an aluminum disc which is mounted on a point which can freely rotate, right? Let's say a cylindrical aluminum disc which is mounted on a spindle, and if you move a magnet near to this let's say this aluminum disc, if you move it in one direction, any of the direction, what happens? This aluminum disc is also going to rotate, right? And if you stop the magnet's motion, if you place it very near to the aluminum disc, then the aluminum disc, if it is in motion, it will come to rest, which means that this aluminum disc or this setup generally does not allow relative motion, right? If one is moving, then what happens? There will be eddy current formation in the disc, and this will oppose this motion, which means that it is not actually opposing the motion, it is actually opposing the relative motion between the aluminum and the magnet, right? Even though aluminum is not magnetic, it will generate eddy currents in it in order to stop its relative motion. Now the same principle is being used in a energy meter as well. So in energy meter we have a large disc, aluminum disc, and now in the previous case we saw the in order to make this cylindrical aluminum shaped plate, to make it in motion, we had to move this magnet, right? We need to move this magnet in order to get the motion for this disc. But how can we do it without having any moving parts? Now if you want to move anything, if you want to move this aluminum disc without actually moving any other magnet or any other physically moving any other magnet or electromagnet, the only way that is possible is by having a rotating magnetic field, right? If you have a rotating magnetic field, then that can also induce a EMF in the aluminum disc, and in order to reduce the relative motion, this aluminum disc can go into a state of motion, right? So here this aluminum disc is generally mounted on a spindle, so which is freely rotatable. So let's see how we can produce a rotating magnetic field. So it's very easy. You just need 3 electromagnets in order to produce a rotating magnetic field. So let's say you have one electromagnet, so let's say this has a current direction in this way. So if you look from bottom, it is in clockwise direction, right? So this electromagnet has a clockwise direction. If you look from the bottom, so clockwise direction means it has a south pole, right? So there is a south pole at the bottom over here and a north pole. I mean, we are talking about AC currents, so this keeps changing, the south and the north poles. But as of now, let's take this assumption, right? And let's say you have a second electromagnet which is having a phase difference of 90 degrees, right? So let's say you have another magnet with a phase difference of 90 degrees, and let's say you have a third electromagnet with a phase difference of, let's call this 1, 2 and 3, right? So let's say this outlet, the wire that is coming out from 1 is joined to the magnet number 3 in the opposite direction, let's say, right? Which means that it will have a phase difference of 190 degrees with respect to 1, right? So let's take this wire over here. So the current is moving in this direction over here, in this direction, which means that while there is a south pole over here, you get a north pole in 3, right? And we have a south pole over here. So if you look at the graphs of these 3 electromagnets, we can see this is having a lagging of 90 degrees with respect to 1. It has a lagging of 190 degrees with respect to 1. So if you look at the graphs, we can see that first, since it's an AC current, alternating current, let's say this is the graph of 1, right? So yeah, so it's not so great. So anyway, so this is the graph of, let's call this as 1. Let's draw the graph of 2. Let's give this as 2. So 2 starts at 90 degrees. This is maximum at yeah. So this is at 2, and let's say this is 3, right? So 3 is having a 180 degree shift. Sorry. Yeah. So this is how the graph looks like. So you can see that as time goes, what happens, the magnetic field of in 1 you have south pole over here, right? And it has a very let's say it has the highest magnitude at 90 degrees. At 90 degrees 2 is having a 0 magnitude graph, and let's say here also you have a south pole that is forming, right? Let's say there is a south pole that is forming at, let's say, at 180 degrees. 2 is at maximum, right? So here you have a south pole for 2 at 180 degrees. Here there was a south pole for 1, and at 180 270 degrees the third electromagnet is having a south pole, right? So here you had a north pole over here for the third magnet, but then it became 0, then it became maximum over here. By the time what happened, 1 has gone to north, 1 has become north, 2 has become north, and again after that 3 becomes north. So what happens is that this, with time, what happens, this magnetic field is continuously rotating, right? Which means that let's say if you place these magnets on top of this disk, what happens, you will get a rotating magnetic field without any physical motion, right? Now if you look at the actual diagram, so you can see, so let's first look at the connections, right? Let's first look at the connections. So basically the 1 and 3 corresponds to your current coil. The energy meter also has a very similar circuit diagram to a very similar to your wattmeter. The circuit is exactly same. It has 2 current coils and 1 pressure coil. That is how it works. And only thing is that it is placed in such a way that it can produce a rotating magnetic field which will enable this disk to rotate, right, in any of these directions. So that is how this is being done. So this 1 and 3 will correspond to your current coil. So let's say this is your supply. You can connect your supply over here, and the current comes through here, and let's say this is connected to your load. Right, now this is your pressure coil, so you can connect your pressure coil to any of these points. Let's say you can connect it, let's say, to one of these points, and the other one you can connect it to the bottom, right? So you can connect it to the load over here, right? So basically this is the same connection as in the case of wattmeter. So you have, let's say, your V1 over here, V2 over here, C1 over here, and C2 over here, right? It's very simple. It's the same connection diagram of a wattmeter. And if you look at the construction, the construction is very simple. So this, you have a disk and you have these 3 electromagnets placed in such an arrangement that it will allow the rotation of this aluminum disc, right? So let's look at the construction. So let's say we'll look at the front view, right? Front view. So the disk is over here. Let's say this is our disk. So if you look at this disk from the front, this looks as a single long bar, because you won't see a disk when you look at it from the front view, right? And what we have is a magnet, electromagnet, which is basically the pressure coil. So the magnet corresponding to the pressure coil. You can look at the diagram in any of the textbooks or even in the internet, because my drawing is not that great. So my job here is to make you understand how it works. And look, the diagrams, it's better if you look at some good books, textbooks, or you can even get it in the internet very easily. So I am drawing a very rough diagram over here in order to make you understand. So let's say your supply, let's say your supply voltage is over here. So the pressure coil comes directly to this branch, right? So and it is connected across the supply, right? And you have your current coils. So this is connected onto a spindle, as we have seen, which is free to rotate. And you have your current coil, at the bottom. And the winding is connected over here. And we know the second winding is in 180 degree phase difference, right? So the current direction changes, and the not the current direction changes, the winding direction changes, because of which you will have when, let's say, when you look from the top, this is a this is in clockwise, so this becomes a south pole, and this becomes a north pole. Yeah. Sorry, this is not winded like this. Let me just draw it once again. Yeah. Yeah, so this is the direction. So this becomes a north pole, so this becomes a south pole over here, because it's in clockwise direction when you look from the top, right? So there's a south pole over here, and you'll have a north pole. But yeah, since this is a alternating current, this keeps on changing. Only thing is that there is a phase difference of 180 degrees. There is no phase difference in the current, but magnetic phase difference of 180 degrees, right? Which means that when a south pole is on this bar, there would be a north pole over here. That's all. So now you have the wire coming out from over here, and the load is connected over here. So you have the load, and the load is connected across these 2 points. So this is how this is being designed. And what we also have instead of spring connect contacts, what we use is a braking magnet, right? So we use a magnet, permanent magnet, in order to provide the controlling torque. So what we have is a permanent magnet placed over here, which will act as a which will give the controlling torque. Is also known as a braking magnet, because the reason is that we don't want this disc to continuously rotate, and because let's say if it shouldn't rotate because of inertia. Let's say once it starts rotating, it should stop the moment there is no energy that is being consumed, right? So we need to have a proper braking when the power flow stops. So what we are going to do over here is that we are going to measure energy, and energy, as you know, is the time integral of power, right? So here if you have a pressure coil and a current coil, definitely it produces a power, and it is going to be a average power that is going to be measured. That is only in the case of when you connect a spring. But in the case of if you don't have a spring, what happens is that this disc keeps rotating. That is the major advantage over here, right? So here we can see that the pressure coil, we have already told that 2 is the pressure coil. It is in 90-degree phase lag, right? 90 degrees phase lag. The reason is that we'll try to get a purely inductive coil, which can have lag of 90 degrees. And here you can see this current coil is in series with the load, and we assume that the impedance of the current coil, is much smaller compared to the impedance of the load, right? Because this is in series connection, so we are not we consider that the current that is going through the current coil is in phase with the source itself, right? Source voltage, let's say V of t is the source voltage, and we assume that it is in phase with the source voltage because the inductance of the current coil would be much lesser in comparison to the load that we are connecting to this particular instrument, right? So that is how we assume that the current coil, the first coil 1 is having a coil 1 and coil 2 has a phase difference of 90 degrees, and coil 2 and coil 3 has a phase difference of 90 degrees, and thereby we generate a rotating magnetic field, right? Now here the braking magnet is not, the controlling torque is provided by the braking magnet, and the controlling torque is modeled as is proportional to the angular velocity over here of the disc. It is not dependent upon the theta, as in the case of spring it was k theta, right? But here it is proportional to the angular velocity, which is d by dt of theta, right? Theta dot means that is the d by dt of theta, right, which is the angular speed. So here what we get is that we can write this as controlling torque as k1 into theta dot or theta dash, and the deflecting torque in this case will depend upon the current ICC and the current through the voltage across the pressure coil, right? So we'll get the deflecting torque TD is proportional to Vc of t or V of t, which is again proportional to IPC of t, and TD is also proportional to ICC, the current coil current, right? So now we know that there is a phase difference between the voltage in the pressure coil and the current in the current coil. So the deflecting torque can be written as the current I or the into the voltage that is applied into the phase difference, cos of phase difference, cos phi. Now which is also can be written as the load power in this case, right? So here phi is the phase difference between I and V. So this is basically the load power that is being measured, or we can write TD is basically proportional to K2 into the power, and TC can be written as proportional to K1 into theta dot, right? So at equilibrium, what happens is that it accelerates the disk, and at some point when the power is no more being consumed, it comes to equilibrium and it stops. So we can equate these two, deflecting torque and controlling torque, in order to just find what would be the corresponding deviations of the disk. So here the deflecting torque would be the time average of power, dt can be written as K1 by K2 integral of theta dot dt. Let's say we can put two time domains, let's say T1 to T2. The power consumed will be from T1 to T2, and which can be written as energy. The energy consumed will be equal to K1 by K2 into theta of T2, or theta 2, you can write theta of T2, theta at T2 minus theta at T1, right? So that is how this deviation happens, or the angle changes, or you can say there is a particular amount of rotation that has happened due to this particular energy consumption, right? And what we do is that we'll be using what you can say, a gear mechanism, right? We'll be using a gear mechanism attached to this disk, and then from there we'll attach another gear mechanism, right? And then we'll convert it into the dials. You might have seen the dials on the energy meter. There will be dials which will keep rotating, right? So this is directly attached to the disk, and the dials keep rotating depending upon the gear mechanism that we have, right? So that is how we design the energy meter, and that is how we implement the energy meter calculations, right? So now let us look at the connections of wattmeter. Let's look at how energy meters can be connected in a three-phase system, and how the measurements can be done for the energy meter in three-phase systems, right? So let's look at a three-phase 4-wire system. I hope you have already learned about three-phase 4-wire system. Sorry for the noises in between. Okay. Now one way is that you can directly connect 3 energy meters, or let's say we are looking at the power measurement, right? 3-phase 4-wire system, power measurement using wattmeters, right? So in this 3-phase 4-wire system, either you can connect 3 wattmeters. The in three-phase 4-wire system, you can directly connect 3 wattmeters onto all 3 phases. And let's look at the diagram. Let's say you have a source, so this is your 3-phase source, and let's say this is your neutral, right, over here, and let's say you have a load over here, right. You have a 3-phase load, let's call it ABC. Line A, line B, line C. So what we do is that, let's say this is your line A, so you'll connect a wattmeter. The current coil will come from the wattmeter directly from the line, and then you'll connect it to the neutral. We'll connect this to, let's say, A, B, C. So let's say the next line that we have, so you have another current, another wattmeter over here in 3-phase system, and let's say you have a pressure coil that's coming from here connected to over here. Let's call this as W1. This is the W2 reading, and let's say this is connected to C, and so this is how you connect, how you will measure the power. So let's say this is W3, so the total power in this case, this is pretty simple connection, will be W1 plus W2 plus W3. And let's say you are having a 3-phase, so this will be the ground. Let's say you're having a 3-phase 3-wire system without the neutral, which means that it's a balanced system where IA plus IB plus IC, the currents, let's say these are IA, IB, the currents, the sum, all the algebraic sum is basically equal to 0. So in that case, you can go for something known as a 2 wattmeter method. So let's look at that as well. 3-phase 3-wire system with 2 wattmeter method. So all these experiments, I think we'll be doing it in the lab as well, which will make it much more clearer. But let's look at how the connections can be done for a 3-phase 2 wattmeter method. So here you have a 3-phase 3-wire system. So this is your phase A, your phase B, and your phase C, right? Now you will use only 2 wattmeters in this case. Now we'll see what is the reason for that. So what we do is that we'll take any of the 2 phases. Let's say this is IA, and phase A, we'll connect the current coil across through the line, and then we'll connect a pressure coil like this over here between A and B, and similarly you can take any of the phases, it doesn't matter which phase you want to put the current coil in, but make sure that the pressure coil is across the other two phases, right? So if you're taking the pressure coil from phase B, then make sure that it is the same way is being done. So you have the pressure coil over here, then you'll connect it to phase C, right? So any one of the phases should be kept as common in this case. That is the main thing that I was trying to explain. So here phase B is our common, and let's say this is A, this is B, and this is our C. So this is the connection that we have done. Let's call this IA, IB, and this current is IC in this case. So here we can see you have two wattmeters. So let's call this as wattmeter 1, W1, and this as W2, which are the two wattmeters. And let's say this is the current coil CC, and this is our pressure coil PC. It's CC pressure coil. Sorry. This is PC. This is the pressure coil, and this is the current coil over here of wattmeter 1 and wattmeter 2. Now let's look at what would be the reading of W1 plus W2. Right, W1 plus W2, what would be the reading in this case? And let's see how we can find the total power in this case. All right, so here W1 corresponds to IA into let's say this is VA and this is VB, right? So the entire voltage over here can be written as VAB, which is VA minus VB. So the pressure coil is going to measure the entire voltage across these 2 points, which can be written as VA minus VB, or you can write it as VAB, that is IA into VA minus VB. Similarly, you have W2, that is equal to IC. The current coil is going to measure the current through the C terminal, or the C you can say C line. So that is IC into, now the pressure coil takes the pressure voltage difference between C and B, so you can write it as VCB, right? That is IC into VC minus VB, right? So what happens over here, W1 plus, if you add W1 plus W2 from these two values, you will get it as, it is basically IA into VA minus VB plus IC into VC minus VB, right? If you expand, you get it as IA into VA minus IA into VB plus IC into VC minus IC into VB, right? Now here in two quantities we have VB common, so let's take it together. So IA VA, we know IAV is the power in the A line, plus IC into BC is the power in the C line. So you have got two powers. Now we'll take minus VB outside, minus VB into IA plus IC. Now since this is a balanced system and this is a 3-wire system, we know that IA plus IB plus IC in this case is going to be equal to 0, or you can say IA plus IC is equal to minus IB. So mathematically, if you look, IA into VA plus IC into VC minus VB into minus IB, this is equal to IA into VA plus IC into VC plus IB into VB will be the power that we get from W1 plus W2. Now here, this is the phase A power, this is the phase C power, this is the phase B power, which is basically the total power, right? So I hope this is very much clear to you guys. So 2 wattmeter method, if you add the values of 2 wattmeters W1 and W2, you will finally end up getting the total power in the system, right? So I think with this we'll wind up the class over here, and we'll continue in the next class. Thank you guys.